Let's review some limits together, including both right and left-handed limits. We'll look at some limits graphically, and we'll do some simplifying algebraically to evaluate several different types of limits. I want to go ahead and start with the right and left-handed limits. But as we begin, let's first analyze what the function evaluated at 3 is. Now, f of 3 is my x value, f of 3 is my y value, and that lines up with a 2. When we're analyzing limits, it's very, very similar, but we're looking to see what we're approaching as opposed to exactly where we're at. I want to start with this limit. The limit is x approaches 3. That little negative means from the left. And as I am approaching 3 from the left, my function is approaching that point 3, 1. Now, limits, just like our function values, give us a y value back. So in this case, our answer is 1. Now in our next one, we're going to approach 3 from the right-hand side. So we're going to look at that horizontal line up above, and that horizontal line is approaching that point 3, 2. So our limit value is equal to 2. Now we're also going to want to know what is the overall limit. So notice there's no superscript plus or minus on this one. This literally means the limit as we approach 3 from both directions. Now we just saw that those land at 2 different places, which means that the limit overall as x approaches 3 does not exist. Let's continue analyzing our limits graphically. Now, in this case, we're going to be approaching 3 for most of them, but there's an asymptote there at 3. I again want to start with f of 3. That's the actual point. The limit is what we get as we're approaching 3. So at the actual value 3, my y value is equal to 2. Now on this one, as we approach 3 from the left, we're approaching that point 3, 1, and our y value, or our limit, is 1. But as we're approaching 3 from the right-hand side, I am coming up to that asymptote, which means that those y values are climbing and climbing without bound. So we can say that the limit is infinity, but infinity really means there is no limit. So you could also say does not exist here. Now, if we take a look at that limit overall, as we're approaching 3 from both directions, they're 2 different values, which means that that limit overall does not exist. Okay, last but not least, the limit as x approaches 2. Now, it's defined at 2, and I take a look at that limit as I'm approaching 2 from both directions. It lands on the same point, the same y value, so that limit is equal to 0. You also need to know how to evaluate limits algebraically. Our goal is to remove the discontinuity with our algebra, and in this type, we want to factor and cancel. Now, the very first thing that you would want to do is to plug 2 in. If I just check it in my denominator there, I get a 4 minus a 10 plus a 6, and I end up with a 0 in that denominator. So I know I've got a discontinuity there. So I want to go ahead and factor this. So I'm going to take the limit as x approaches 2. In my numerator, I can factor that difference of squares as x plus 2, x minus 2. And in the denominator, I can factor that trinomial into 2 binomials. X will do minus 3x minus 2. The order doesn't matter. X minus 2. Now I notice that I've got x minus 2's in both of them. So this gives me now a limit of an expression that's equivalent everywhere except for 2. So I've got x plus 2 in the numerator, x minus 3 in the denominator. If I attempt to plug 2 in now, I get 2 plus 2 over 2 minus 3, which is equal to 4 over negative 1 or negative 4, and we've got our answer. Limits of functions with radicals is another common one that you're going to need to know how to simplify. If I attempted to put 5 into the denominator here, I end up with the square root of 9 minus 3, and I get a 0 in that denominator. So I again want to remove this discontinuity, and I'm going to do it by multiplying through by some conjugates. So I'm going to take this limit. I've got x minus 5 in the numerator, and then the square root of x plus 4 minus a 3 in the denominator. I want to multiply by the conjugate of that radical expression. So I'm going to go ahead and change that radical expression so it has a plus in the middle. And I'm going to multiply this top and bottom. So I get the square root of x plus 4 plus a 3. Whatever I do to the denominator, I've got to do to the numerator as well. So I get another plus 3 there. Now, I am not going to completely multiply things out. I'm going to go ahead and leave the numerator, but I do want to simplify that denominator. So leaving that numerator, x approaches 5. I'm going to leave that as x minus 5. Square root of x plus 4 plus 3. Let's go ahead and FOIL through that denominator. As I FOIL through the denominator, I'm going to multiply my two radicals together. So that's going to be the square root of x plus 4 squared. As I multiply the inner term and those outer terms together, they end up canceling each other out. So I can go ahead and multiply those last two terms together. Negative 3 times 3 is going to be minus 9. Now, continuing to simplify that denominator, this denominator becomes x plus 4 because the square and the square root cancel each other out. I get x plus 4 minus 9, which I can rewrite as x minus 5. We end up with the limit as x approaches 5. You'll see why I did not multiply through that numerator, square root of x plus 4 plus 3. It's because I ended up with that x minus 5 in the denominator, and I'm able to cancel it. I'm removing that discontinuity at 5 by canceling the x minus 5s. Now that I've got this equivalent function that is no longer discontinuous at 5, I can go ahead and just plug 5 in. So plugging 5 in, I get the square root of 5 plus 4 plus 3. Square root of 9 plus 3, that's going to be 3 plus 3, or 6. We also have complex rational expressions. So we've got these fractions inside of this fraction, and we want to remove that discontinuity at negative 3. We're going to do that by clearing our denominators. So for this one, I've got the limit as x approaches negative 3 of x over 1 over 3 plus x. That's where that discontinuity comes into play. It's undefined there at negative 3, minus 1 over x. Now to clear my denominators, I need a lowest common denominator. My denominators are a 3 plus x and an x, so my lowest common denominator is going to be their product, 3 plus x times x. And I'm going to go ahead and take everything in the numerator, it's just an x, and I'm going to multiply it by 3 plus x times x, and then I take everything in the denominator and multiply it times 3 plus x times x. Now I've done this so I can cancel those denominators. So as I multiply things through in the denominator, I'm not going to mess with the numerator. I've got the limit as x approaches negative 3. I'm going to leave this as I've got an x times an x, so let's call that x squared, 3 plus x. And then I'm going to multiply through 3 plus x times this fraction, 1 over 3 plus x. The 3 plus x's there are going to cancel and leave me with just the x. So I'm going to end up with just the x for that one. Let me get rid of that. So I've got just the x there. And then I do the same thing with my second fraction. I'm going to multiply through by my 3 plus x times x. In this case, the x's are going to cancel, and I'm going to have that 3 plus x multiplied by that negative sign. Now let me clear this up so we can put that there as well. So I have minus parentheses 3 plus x. As I simplify this, I get the limit as x approaches negative 3 of x squared 3 plus x In the denominator, I get x minus x. That's going to be 0. And then I've got that -3. So I can see that this took care of my discontinuity at -3. I can go ahead and plug -3 in now to evaluate. So I get -3 squared. 3 plus -3, which is 0, all divided by -3. And we end up with a limit that's equal to 0. Keep up the good work. Take a look at this video that I've got for you next.